Hello, everyone, and welcome to today's webinar. My name is Chris Neva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenter today is Joshua Prey. Joshua is a Senior Engineer and Product Manager at Thermal Analytics. His primary focus is developing models and simulation processes using TAITherm, CFD, and other CAE tools, including applications such as climate control and thermal comfort, vehicle thermal management, and surrogate modeling. Mr. Pryor has been with Thermal Analytics since 2006 after receiving his BS in Mechanical Engineering from Michigan Technological University. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We are also recording this webinar and we'll be sending you the link following this presentation. And with that, Josh, if you're ready, you may begin.
Great, thanks Chris, and thanks everybody for joining our webinar today. And yeah, as you're aware, we'll be talking about how our TAITherm and RapidFlow products can be used for cabin simulation. And we're gonna show a number of examples of using those products for that application and how some of these kind of new methods in our software compare to existing methods we've been using for cabin, and try to help you understand some of the attributes of different methods and choose the right one for your simulations. So to set some context of why we're interested in cabin simulation, for anyone doing roles related to product development of automobile or other industry cabins, and by cabin here we just mean some sort of occupied space that's designed to have human occupants or other thermally sensitive objects within it, and that space is going to be thermally controlled at some time. If you're doing design of those, you might want to understand the details of climate control, the thermal comfort of the occupants, and what sort of requirements or performance you see for the HVAC system that's being used. And simulation is, of course, a great tool for doing that. And with recent industry changes, we certainly see more focus on simulation for cabin and focus on new attributes and key questions. And a lot of that is being driven by electrification in the auto industry and some energy management concerns that come along with that, especially around the impact of cabin energy on vehicle range, and the fact that without internal combustion, we no longer have free waste heat to heat up the cabin. There's also a lot of interest recently in using microclimate devices, things like heated contact surfaces or radiant panels, to kind of focus the energy used on what we actually care about heating or cooling, and not such a broad strategy. And also a lot of interest in understanding control strategies and designing them more in the simulation stage. So how can we, again, reduce energy or reduce the user customization needs by having HVAC control algorithms that focus more on the human occupants and what they're perceiving and really optimizing for what we care about. So simulation can help us with all of those needs. And if we're going to do comprehensive cabin analysis, we really need to understand both soak modeling, sort of the preconditioning that we see happening when the cabin is unoccupied and being affected by the ambient environment, and the transient warm up or cool down scenarios once the vehicle or cabin becomes occupied and we care about how quickly we can achieve comfort or the conditioning of the cabin. So to paint some of that context from some articles in the news, got a few examples that kind of point to some of this interest. The first here is an example article talking about the use of electric school buses in cold weather climates. And I've highlighted a couple notes here that talk about the benefits of using heated driver seats to not have to cool the entire bus, but in some cases still needing auxiliary fossil fuel heaters alongside the battery, and the benefit of preconditioning the bus and not using the battery to do that conditioning after the vehicle starts driving. So again, simulation can help us here to understand those situations and perhaps predict when they're necessary and the right strategies for them. Similarly, for conventional cars and vehicles, there's an article here about electric cars and winter driving and range anxiety, and highlighting again here that even for end users, there's a lot of focus on the effects of ambient temperature and strategies to mitigate that in terms of, again, preconditioning the vehicle and using the different HVAC system attributes a little bit more intelligently. And perhaps, again, simulation can help us take away some of that burden from the end user and the anxiety they've got associated with that. And then a little more from the scientific side of things, there's an article here that talks about some recent advances and different design options for air heating systems for electric vehicles. And the table that's highlighted here talks about the many different types of heating systems that might be applied for an EV, going all the way from PTC systems to vapor compression and to more novel concepts like waste heat recovery or even thermoelectric devices. So if we're going to be considering all of those in terms of the HVAC system design, of course, we want to understand how they're going to impact the cabin and the comfort of the occupants. And again, simulation can help us with those problems. So again, we're going to be talking about how RapidFlow applies to these problems. So starting off with what is RapidFlow? It's one of the newest product extensions for thermoanalytics TAITherm or Musis thermal solvers. It's a 3D flow solver that's designed specifically to help you with heat transfer problems where there's an airflow aspect to those problems. It's intended to give you fast but high fidelity results when you want them with a flexible level of detail in the flow simulation, and to work with any sort of complex 3D surface geometry you'd already be making use of in a TAITherm cabin model. We want it to be easy to use, both in terms of the time investment for setting up and configuring the solver and making the volume meshing as automatic and hands-off as possible. And of course, tightly integrated with our thermal products. So even though we're with this extension, we're solving a fluid domain separately from the thermal domain and coupling them. That all happens behind the scenes. And once RapidFlow is configured, just when you run your TAITherm or Musis model, all of that happens in the background. So more of a single software solution. We'll show a bit more about how all this works. In terms of specifically how we reach those attributes with how RapidFlow is designed, I've got a slide here to summarize some of the key attributes of this extension as of our latest 2024.2 release. In terms of the physics assumptions, we start from simplified Navier-Stokes governing equations for the fluid domain. We simplify them down to be both incompressible and inviscid flow, reducing the complexity. We do include optional models for Rand's turbulence using a simple mixing length approach, and buoyancy effects using a simple Boussinesque approach. So again, trying to use fast and simple models, but still include the physics that are necessary for some of these applications. In terms of the solver, we do a couple of novel things with RapidFlow. The advection part of the problem is solved with a semi-Lagrangian approach using sort of temporary particle transport rather than solving for something like momentum equations. The solver works on an inherently transient basis using time split equations. And we'll talk more about how the inherently transient nature is used for different kinds of problems. With the way the fluid equation is being solved, especially with that semi-Lagrangian advection, the interpolation of quantities within the mesh is really important for accuracy. So it includes both the default cubic higher accuracy and linear interpolation to get that right. And in terms of the performance of the solver, it runs in distributed parallel on many CPUs, either on a workstation or HPC. And in the future, we'll have more options for running this fast, including GPU. For the geometry and meshing of RapidFlow, again, we try to do that automatically based on the thermal mesh that you'd already have as part of your TAITherm model. And that involves just setting the seed points and generating an internal or external flow domain automatically based on user parameters. The geometry that bounds the fluid domain can be defined both by solid single-sided walls and baffle or two-sided thin shell walls. The baffle support is a new feature as of the 2024.2 release. And again, we want to be flexible in terms of cell size, depending on the amount of fidelity or the simulation performance the user wants. We can use pretty coarse or pretty fine cell sizes correspondingly. For the boundary conditions that you specify, you can set up any number of inlet and outlet flow boundaries on the RapidFlow side based on thermal parts, again, on the TAITherm thermal mesh. The inputs for those boundary conditions can be specified as constant values, transient curves that are set up in the thermal model, or dynamic input parameters, allowing those to be scripted or coupled to third-party tools. We'll talk a little bit more about how that works. And then in terms of the coupling between fluid and thermal, it's the automatic two-way mapping and coupling between the domains. We provide options to allow you to do efficient, steady, transient, or pseudo-transient coupling. And by pseudo-transient here, we mean if you have a problem where the timescale of the thermal domain is much longer or different than the fluid domain, then you don't have to march forward in time on the fluid side for the entire duration. You just have to march forward far enough for the flow field to be properly converged, and we can still sync up the coupling properly. And then in terms of the convective conditions that are the kind of key thing being mapped from the fluid domain, the way those are correlated to the near wall flow field also has flexibility that the user can customize. To further illustrate some of the workflows of using different cabin modeling options, I've got a few graphics here. This first one shows what it might look like to set up a TAITherm only cabin modeling workflow, where we would start from some CAD geometry, simplify and prepare that geometry to represent a good thermal mesh focusing on the cabin domain. Preparing that thermal mesh might be automated to various degrees, but that's often going to be associated with some amount of user time and a small amount of computational time. And then once we've got a TAITherm model, if we're using TAITherm on its own without any fluid solver, we might represent the air inside the cabin as just a single bulk fluid node, kind of represented by the green dot in the graphic here. And that model would have the advantage of being pretty low in terms of computational cost, but will, of course, not give us the high fidelity air flow and temperature results we might be interested in. So, of course, for applications where we want that fidelity on the airflow side, the other kind of long-standing simulation method would be coupling TAITherm to an external CFD model. And that's going to be associated with some additional mesh preparation for the CFD model that often would be split off from the thermal geometry preparation at some point in the model workflow. That would be associated with at least some additional user time and computational time to generate the mesh. Once we've got that, that'll give us a nice 3D representation of the air inside the cabin, but that's of course going to add a substantial amount of computational cost to what TAITherm is doing on its own. And then to bring those models together, we're going to need something like a cotherm coupling process or other coordination to do the coupling. That's been pretty streamlined over recent years, but there's still going to be some amount of user time with setting up that coupling. But that's going to give us full 3D results in both the thermal and fluid domains. And we don't expect either of those previous two workflows to be going away anytime soon. They'll still make sense for various types of problems. But what we're really trying to do with RapidFlow is provide a little bit of the best of both, where the model preparation workflow is still very similar to what you would do with TAITherm on its own. You might pay a little bit more attention to what the flow boundaries are and whether they're parted out, and perhaps the definition of that domain, but overall the requirements of the TAITherm thermal mesh don't change very much at all. By activating the RapidFlow model, as mentioned, we kind of generate a fluid mesh automatically from the thermal mesh. So that'll give us the same sort of 3D flow and temperature discretization inside the cabin. And in this case, the coupling between thermal and fluid is automated, so kind of reducing some user burden there as well. So hopefully with a more modest computational cost and reduced user pre-processing time, we can achieve the same or similar level of fidelities to the CFD coupled approach. To illustrate a little bit more about what it looks like to set up RapidFlow for a cabin model, the starting point again would be preparing a TAITherm thermal mesh of the surfaces representing the cabin and any human occupants as you normally would. We're showing an example model here with a cut plane kind of put down the middle of the cabin. Then to set up the fluid coupling, you add what would normally be a 0D bulk fluid node with a defined position inside that, the location where you want the fluid domain to be. But in this case, by giving that part name a particular name, which is fluid_simulation, and by adding a text config file alongside the thermal model that'll specify some of the parameters we need for the RapidFlow solver, that will activate this RapidFlow modeling and the coupling to the thermal domain. So once that fluid part has been created and the text file is in place, then it's just a matter of connecting all of the surfaces that you want to participate in the RapidFlow fluid domain to that special fluid part by any convection method, and then they'll be recognized to participate on the fluid part of the problem. So then what will happen at runtime is starting from that seed point and using the surfaces that have been chosen, We'll flood the domain with the cell size that the user has requested to recognize the volume domain. So the blue cells you see here in the animation are what will end up being used for the cabin fluid domain. So getting into some of the scenarios we want to run for cabin, starting off with soak or preconditioning modeling and some of the considerations that go along with that. Again, for the motivation, we want to model these soak scenarios for a couple of reasons. Very frequently, we just want good initial conditions if we're going to simulate a transient warm up or cool down following the soak. And if we're going to get the aspects and outcomes of that model correct, then we need good initial conditions. But even inherently within the soak, there might be some interesting thermal management needs for things like sensitive materials or electronic components that have temperature limits that might be encountered during a soak. And also understanding details like touch temperatures for humans as they enter the cabin initially. Modeling soaks can be challenging because all of the modes of heat transfer are pretty important to get things right. Obviously, buoyant flow and natural convection creating vertical air temperature gradients. The radiation effects, both shortwave and longwave, through the glass and within the cabin, and those two working together to kind of create the greenhouse effect and temperature gradients. And we also need to understand the conduction through the cabin walls and the complex stack-ups that those sometimes consist of to understand how heat comes into and out of the cabin. Those temperature gradients within soaks driven by natural convection can be pretty difficult to model without some sort of 3D fluid dynamics. But it's often somewhat impractical to do a full conventional CFD simulation for the very long transients, 4 to 10 hours or beyond that we might have within a soak. So putting all that together, RapidFlow is a good fit for doing some of the cabin soak modeling. We can bring in a 3D fluid model and use a fairly coarse discretization so things still run reasonably fast. And we can use the buoyancy and turbulence models mentioned earlier to capture the physics we care about and sort of tune, again, the fidelity or runtime that we want out of a soak. We've got an example model we'll show here with using TAITherm and RapidFlow for a soak using a simple, fairly low resolution SUV cabin model. This model does include enough of the interior details, the trim, dash, seats, and steering wheel to understand heat transfer during the soak. And for this scenario, we're going to do a 6-hour soak in a Phoenix weather condition with the vehicle facing south. The chart here shows the ambient temperature and solar load that are increasing over time during that soak. And we're going to model this with as if it's in a true natural environment with the sun position moving over that condition. For using RapidFlow with this model, we're going to set up the model with some typical parameters that we might for a cabin soak. In this one, we're going to use a 50 millimeter cell size, which will give us about a 25,000 cell count domain. And we'll show a little bit of the sensitivity of different sizes in a couple of slides. The model will have the RANS mixing length turbulence model and buoyancy models turned on. We'll use a somewhat higher CFL condition to speed things up a little bit, around 2.5. RapidFlow tends to be stable for very high CFL conditions, as high as 10 or 20, but you get the best accuracy the closer you get to 1. And then the last couple of bullets here get into some of the pseudo-transient coupling parameters that are pretty important. So for a soak modeling case, having a tight coupling between the thermal and fluid solve is pretty important. So on the TAITherm thermal model side of things, we're going to use a fairly small time step size compared to what you normally would for a soak, which might be several minutes. But with coupling here, we're going to use about a 15-second TAITherm time step size. And then for each one of those TAITherm time steps, we're going to let the RapidFlow fluid solver march forward up to a maximum of 2 seconds, or even less than that if we hit a specified tolerance. And those values were found to be sufficient for most time steps to let the fluid domain converge appropriately for how the thermal boundary conditions, surface temperatures have changed. And again, these are all values that you can tune a little bit to trade off between accuracy and runtime. So here's an animation showing a little bit more of the boundary condition side of things. This is coming from TAITherm, showing the solar load on the vehicle, absorbed solar load over time. So with that vehicle facing south, we've got the high solar loads on the driver's side of the vehicle initially, and then slowly moving towards the front and increasing in intensity. And here's an animation showing some streamlines using the RapidFlow fluid predictions inside. And these may be a little bit difficult to see with this animation, but the point here is we've got some different sort of natural convection cells forming over time. Initially with that high solar load on one side of the vehicle, we get some asymmetric behavior. But then as the sun kind of moves towards the front of the vehicle, we get some more symmetric natural convection cells with a lot of the hot air rising up the windshield towards the headliner and falling back down. And again, understanding the flow patterns here and how they drive the air temperature gradients locally in the cabin is what we're trying to get out of this. Next, I've got a similar animation showing two different cut planes through the RapidFlow domain, and you can see how the coarse grid there overlays the original thermal geometry, and we're just showing the temperature on those planes over time. So once again, here you can see how the high temperatures and temperature gradients are progressing and how the solar heat is driving the locally high air temperatures, especially late in the soak here along the headliner and windshield. I'll let that play through close to the end here one more time. So then showing some transient results from the thermal side of things using those fluid conditions mapped and coupled onto the TAITherm domain and animating the surface temperatures over time through a couple of different cut planes looking at the cabin interior. So again, we can see here how the local peak temperatures are developing, influenced by, again, all the modes of heat transfer. So then for a soak condition, we can compare using the RapidFlow approach to a typical simpler approach, which might be using a network of fluid nodes. So on the right side of the slide here, we've got kind of a snapshot in time from the end of the soak, where the lower image shows the predicted temperatures on a simple network of fluid nodes, and the upper image shows a cut plane through the RapidFlow domain. And we can see if you kind of look at the trends and range of temperatures within the area, the bulk nodes are doing a reasonable job of representing the appropriate bulk temperatures associated with those different regions, but they're certainly not capturing some of the local min and max temperatures within each region or across the cabin. And then the image over here on the lower left shows a temperature delta between those two methods, where the scale here is -5 to +5. So blue temperatures are areas where the predictions were colder using RapidFlow 3D flow modeling, and the yellow, orange, red are areas where that was hotter. So again, if those local temperatures are important, then we're seeing some benefit in using the higher fidelity simulation. Then on this next slide, I've got some data summarizing the performance of the solver under different conditions. So some of the important factors that will dictate runtime when using RapidFlow for a soak are, of course, the cell size for the fluid domain, the time step size for the thermal model, which again, we need to keep fairly low to have a good coupling between thermal and fluid, and some of those fluid coupling parameters, including the transient duration, how much are we running the fluid solver for each thermal time step, and some secondary parameters around CFL conditions, apparent area settings, and the tolerance for the flow solver. But then we've got two tables that kind of show performance with different RapidFlow cell sizes. The one on the left is the model we've just been looking at in the previous slides, a low resolution thermal model, just about 25,000 elements. And of course, this is lower resolution than you would often use for a production scale model, but this kind of illustrates the sort of ceiling of performance you could get without having any bottleneck from the thermal solve. That model configuration, if we run it with only fluid nodes, runs about 45 times faster than real time, so very quick. And that's just kind of a benchmark compared to adding RapidFlow in. So with a very coarse cell size of 75, we can still run about 24 times faster than real time. At 50 millimeters, which is where most of our animations were being taken from, that's about 18 times faster than real time. And going all the way down to a 25 millimeter cell size, that still leaves us about 5 times faster than real time. The table on the right is from a somewhat more realistic thermal model resolution size, a model with 600,000 elements for the thermal mesh. There, with fluid nodes only, with the thermal solution requiring a lot more. And with this table, we're using 24 CPUs for the computation, where the one on the left was just 8 CPUs on a desktop. But in that case, with fluid nodes only, we were about 4 times faster than real time. With RapidFlow and 50 millimeter cells, that takes us down to 2.3 times faster. And even with 35 millimeter cells, that remains 2 times faster than real time. So even for a very long soak, with a reasonable workstation or a small HPC, can turn these models around pretty quickly. All right, so switching focus to a cool down modeling example. We're going to show a different model here, again, using an SUV model for a transient cool down condition. This model has a single human in the driver's seat, and we're going to look at a transient cool down again, in a Phoenix weather condition with fairly high ambient and high solar load. And starting from a simple initial condition, we're going to look at panel and second row flow from the HVAC system in full recirculation mode and see what happens over a 45-minute cool down. And in this case, we're going to compare that same cool down using the same TAITherm model with 3 different convection modeling methods. And for all of them, we're going to be specifying the same flow boundary conditions from the vents into the cabin. So for all these methods here, we're kind of taking the simpler approach of just modeling the flow from the vents into the cabin and not trying to model the full detailed flow within the HVAC system and considering the registered geometry. That would be a method, that would be an option for our more advanced 3D methods. But for this study, we're just looking at the simpler approach that'll keep things a little bit faster. Our first method, the simple fast running one, is again going to be using TAITherm without any 3D fluid representation, but just using a single bulk fluid node to represent the bulk temperature of the cabin. With that single bulk fluid node representing everything in the cabin, we're still connecting the same airflow and incoming temperatures from the HVAC system to cool that down in the same way. And we're using the simple library correlations built into TAITherm to represent the convection conditions. And again, that'll give us a very fast running model, but not any 3D airflow effects. Then our high fidelity method will be using an external CFD model coupled to the TAITherm simulation. And we're going to coordinate that with Cotherm in a typical fashion for a transient coupling. That CFD model will use pretty typical practices for a cabin model. We're using ideal gas models and a realizable K-epsilon turbulence model. You can see in the snapshots here, we're using a polyhedral mesh with fine cells near the wall, resolved boundary layer, totaling about 13 million cells. We're going to be doing the coupling with a steady state initial flow solution that we then freeze during the transient cool down. So during the cool down, we're assuming the flow remains the same and only updating the thermal field and coupling that with TAITherm over time, which of course is a pretty efficient method when you're not worried about changes in the flow field during the transient. And then finally, we'll have our RapidFlow convection method. So same thing here with trying to represent the fluid domain in 3D, but using RapidFlow. Here we'll show the trade-offs of a few different cell sizes, but our initial configuration is going to use 18 millimeter cells, which gives us about 3 million total cells. We'll be using the RANS turbulence model and a CFL condition of 1. And just like the CFD coupled case, we'll look at running an initial flow calculation and then freezing that flow during the transient. But here with an inherently transient solver, we need to specify a duration to represent that initial steady flow condition. Our baseline configuration will be 5 seconds to represent that steady condition, and we'll show some trade-offs of that value as well. So once we've got the flow models up and running, we might want to do some comparisons between the 3D flow predictions of CFD and RapidFlow to see how well they compare. And we're doing that on this slide with a few different images. The first column is an isosurface with velocity of 3 meters per second. The second is an isosurface with 2 meters per second, and the third is a streamline image. And the top row of images come from our CFD prediction, and the bottom row come from RapidFlow. So using the same boundary conditions, we'd expect to eventually see the same plumes and effects within the cabin. So you can see the plumes here from our 4 different vents on the panel, 2 in the second row, and you can also see some higher velocities near the recirculation return in the front here. Comparing these isosurfaces, we see some pretty reasonable comparisons with the higher velocities, perhaps some more differences with the lower velocities. and especially looking at what happens after this flow impinges on some surfaces or interacts with the humans. Some of that is perhaps to be expected with the simpler turbulence modeling approach that we're using on the RapidFlow side of things. Some of it is also perhaps due to the fact that we are using a somewhat coarser resolution for the RapidFlow approach than we are for CFD. And you can see some of the same effects here in the streamlines in terms of the velocity ranges within the domain and some of the attributes we see as that flow interacts with different human or cabin surfaces. But beyond just what the flow models are doing, again, with a focus on thermal and comfort modeling, we want to understand how those boundary conditions essentially affect the temperature and comfort predictions. So we might look at some transient plots like the ones on this slide. The top three here are surface temperature predictions for different interesting locations within the cabin. And for each one of those, we're showing the TAITherm standalone method with a fluid node in the dotted line, the TAITherm and CFD coupled method with the dashed line, and then TAITherm and RapidFlow in the solid line. And then the bottom two plots are using the same approach for the three different methods, but looking at thermal sensation predictions using the Berkeley model for the driver occupant we've got in the cabin. Here looking at the neck and left thigh local sensation. And these are just some example plots to kind of paint the context that, you know, for some of these locations, maybe we can get a pretty good prediction with all three methods, including our very low fidelity convection approach. And for some locations like this comfort plot or perhaps this temperature plot, we'll see pretty good agreements between both of the 3D convection methods, but a significant difference from the 0D approach. And then maybe we'll see some other plots like this middle one or lower left where the use of RapidFlow improves the prediction, assuming that the high fidelity CFD prediction here is our sort of reference, you know, without having test data to look at here, but doesn't quite align exactly with that prediction. And just setting that context to explain in the next slide how we're going to compare and judge the benefits of different methods. So starting from those baseline parameters, we could then look at how much further we can optimize the runtime of RapidFlow based on some of those key parameters. So this slide shows the effect on those iso surfaces of velocity using different durations in RapidFlow for that initial flow solve. So the shorter the duration is, the faster that'll run, obviously, and the closer we can get to the reference, the faster the turnaround will be. So the CFD image is up here in the upper left, and then we march down from 10 seconds to 5, 2.5, 1, half a second, and 0.2 of a second. So this kind of gives you an idea of you can use a fairly short duration here and still get, you know, perhaps as short as 1 second and still get predictions that are matching pretty well with the longer duration. We could also look at that same dependency of the duration of the initial RapidFlow solve on those streamline images and get a sense of how the kind of interaction with the human in the cabin changes as we reduce that duration. And once again, until we get all the way down to very short durations, there's not a ton of degradation. So then on this chart, we are trying to compare both the runtime and the accuracy of using those different duration parameters. So the chart here on the left is showing performance, and each bar here represents a different simulation configuration that's split into the time taken for that initial flow solution in blue, and then the total amount of time for the thermal and fluid solvers to run the transient coupling in orange. And the first bar here is our coupled with CFD case, and then 6 different variants of RapidFlow using shorter and shorter durations. And the numbers here show how much faster each one of those is relative to the CFD benchmark. The y-axis here is in seconds, but the ticks are at 1 hour between. And then the bar chart here on the right is trying to show how the accuracy for those cases also change. And here our reference is sort of comparing our 0D fluid node only model to CFD. And what we did is we have 17 total comparison points, similar to those charts shown a couple slides back. And we kind of split them for the fluid node case into the green section represents locations that matched very well between the two simulations, and the red are areas that did not match well. So even with 0D without any 3D fluid dynamics, we can match the reference CFD prediction about 7 out of 17 times. So that's kind of the floor. Once our accuracy approaches that with RapidFlow, we're no longer getting much benefit. And then for these 6 different RapidFlow configurations, we're splitting them into 3 groups. The red, again, being areas that did not match well at all, green being a very good match. And the light green here represents cases where there was improvement in the prediction, but not quite a close match between CFD and RapidFlow. So of course, the larger the dark green, or to some degree, the lighter green bar is, the better this is. And again, kind of similar to the flow images, there's not a lot of drop off in accuracy until we get to the very low durations here. So even with a 1 or 2.5 second duration where we're 18 to 30 times faster than CFD, we can still capture a lot of the same accuracy effect. So again, trying to give you a sense of how the trade-offs can be tuned when using this approach. Then we could also do the same sort of study with changing, rather than the duration, the cell size. So using, in this case, kind of holding that 5-second initial duration constant and changing the cell size for RapidFlow, starting from 18 millimeters and kind of increasing by 6 millimeters in each of these 6 cases, we can see how the flow predictions drop off. And again, as we get, the first few changes don't have too much impact, but as we get into the coarser meshes here, eventually the mesh is too coarse to even capture the size of the vent, size and shape of the vents at the inlets very well. So even the initial shape of these plumes as we get to very coarse meshes doesn't match our reference CFD very well. And then another slide here showing the effect of on the streamlines of these different cell sizes. And then one more chart like the previous, showing both the runtime and accuracy trade-offs. So here with our kind of baseline 18 millimeter cells and 5-second duration, about 12 times faster than the reference CFD. And that can ramp all the way up to 50 to 60 times faster with these coarser cell representations. And we do start to see significant drop off towards the end here. This 48 millimeter cell size, not really too much benefit at that point compared to just using a 0D representation, which would be, of course, even faster. But even in the mid 30s, low 30 millimeter cell sizes, we're still seeing significant benefit and fairly close alignment with the CFD coupled predictions. So wrapping up that cool down example model. So by using the RapidFlow approach for the cool down scenario, we can provide a higher level of fidelity and accuracy, but get some significant reductions in pre-processing and computational cost relative to sort of our CFD coupling benchmark. And kind of shown from some of those bar charts, we can tune that trade-off between accuracy and runtime. So especially if you're working in kind of an earlier design stage and fast is really what you want to optimize for, you can choose that and go with a finer cell size when you can tolerate a little more runtime and need higher accuracy. But higher level, choosing the right modeling technique among all 3 options all 3 are going to be viable for different situations depending on the objectives, the inputs, and the urgency that you're dealing with. So to be a successful analysis team, it might be pretty important to have this variety of methods available and be able to deploy the right method when it's the right choice for the problem at hand. Another attribute we wanted to mention here is coming back to how we connect RapidFlow to things like system models or control algorithms or other dynamic conditions. So I mentioned a while back that the inlet boundary conditions can be specified in several different ways. You can just give a constant value directly in the config file for RapidFlow. You can use a transient curve set up in the TAITherm model, or you can now use input parameters, which is another TAITherm concept. This is a fairly new feature, so if you're not familiar, this is a way to specify a parameter as sort of a placeholder in the TAITherm model, and then that value can be set by an external model or a user script in a dynamic way. So once you set the boundary conditions with an input parameter, you could export the TAITherm model as an FMU representation, and you could then couple that to any of the many system models that support the FMI FMU standard. You could also write a user script directly within TAITherm in Python or JavaScript to set the values, or you could use the co-simulation library, which is a C++ library that allows you to control launching and coupling with TAITherm in the background of some other code you've got. So the application benefit of this is kind of taking this fast and easy fluid capability and being able to leverage it to do things like coupling with a detailed system model to give us better boundary conditions and a more realistic scenario for the application. This would also be useful for looking at control algorithm development. So trying to understand how we can use human-centric or sort of modern smart HVAC approaches to better control what the HVAC system is doing. And now you can put this 3D simulation into the loop of that and understand all of the thermal and comfort details, or any other sort of dynamic behavior that you're not going to be able to prescribe upfront for a simulation that you just want to write some code to understand. So that's another layer of flexibility that's available with the latest release. Looking forward with RapidFlow, wanted to mention a couple of the features that will be continued to develop with this. With the same sort of schedule that we're on for TAITherm and Musis, 2 releases a year, typically April and October. With each one of those, we're adding new features to the RapidFlow extension. Again, for the release that just came out a few weeks ago, there was a substantial improvement in the geometry support, in that 2-sided thin shell baffle geometry, which is pretty commonly used in the TAITherm world, can now be fully set up with RapidFlow, and you'll get the appropriate flow behavior and correct coupling with different conditions mapped onto either side of that 2-sided thin shell. And those improvements also improve the accuracy of the mapping that we're using for any geometry, not just baffles. And that version, of course, includes everything else that we mentioned and showed up today in terms of the distributed parallel performance and the different physics models for turbulence and buoyancy and input options. Some things we have planned for future releases. A big one we'll be working on is a boundary refinement or multi-level mesh capability. So everything we showed here today for cabins was using what we call the Cartesian domain for RapidFlow, which is almost what we always use for that domain. You might be familiar if you've looked at RapidFlow already. There's also an idea of an octree domain that we tend to use for applications like wind flow modeling around large length scales. And one of the advantages of that domain is being able to use a variable sized mesh, whereas the Cartesian mesh currently uses a constant cell size. So the finest level of detail in your model sort of dictates the size and the complexity of the overall domain. But we're working on features that will sort of resolve those and bring a variable mesh size refinement capability to the Cartesian domain alongside all of its other benefits of stability and additional physics models. So especially for cabin, what that will enable quite a bit is, again, the ability to more efficiently set up cabin cases where it's not just the flow from the vents into the cabin, but the flow, including perhaps the full HVAC ductwork and register louver geometry and details like that. We also plan to extend the moisture solver capability that's in TAITherm and include moisture transport and humidity effects within the RapidFlow domain, perhaps alongside a general species transport capability. And that would allow you to understand the local effects of humidity and moisture and look at its impact on comfort and defog, demist applications like that. We plan to further speed up the solver by running on GPUs using some of the same infrastructure that's already in place now to run on distributed parallel. And those sort of mesh refinement features, eventually we want those to be based not just on the boundary geometry, but adaptive in the sense that a RapidFlow model can recognize where higher gradients of values are within the domain and automatically refine the mesh to give you an optimal accuracy and runtime result. So all those will be in the works for future releases. If you're interested in getting started with RapidFlow, materials such as the user guide and example models, simple example models that are shown on this slide are in part of all recent installations of TAITherm. The extension is feature licensed, so to be able to run a model, you will need a feature license in place. But you can work with any of your typical account or support representatives to get that up and running for an evaluation or ask further questions about how that applies to what you're working on. So wrapping things up, we believe RapidFlow and its 3D airflow modeling capabilities, tightly integrated with TAITherm, add a lot of value for looking at these cabin applications. So if you combine the kind of existing capabilities TAITherm brings to the table around thermal modeling, human physiology and comfort, and representing the environment, and now 3D airflow integrated with that, it gives a pretty comprehensive capability for cabin. Due to the kind of flexibility of the solver, we can apply it well for both cabin soak preconditioning and transient scenarios. And due to the design of the solver, we again can optimize some of the inputs to focus more on the fidelity, high accuracy side of things, or the rapid runtime side of things, and allow you to reduce time spent on pre-processing and defining the domain properly when you don't want to focus on those details as much. Thanks everyone for sticking with us and going through this so far, and we can take any questions you've got now.
All right, thanks, Josh. Yeah, we'll open up to some questions here. Can RapidFlow also be used for external flow around vehicles?
Yeah, good question. Focus, of course, here was for cabin. This animation here right at the end, we are showing a simple example of using RapidFlow for both the internal and external flow. You can use RapidFlow for two different domains within one model right now, where one is defined by a fluid part and one is defined by a sort of external airflow configuration. The main focus of that is just for representing convective conditions on the outside. Right now with RapidFlow, we're not doing detailed modeling of components like heat exchangers and fans. So with a higher focus on that, that might not make sense. But for just improving the convective accuracy on the outside of a vehicle, it can be used for that.
All right, thank you. Apart from the air velocity, is it possible to know the level of error in HTC between full CFD and RapidFlow?
Yeah, good question. Of course, the best way to do that would be to have some measurement data to understand the impact. And yeah, especially if, of course, you're probably not going to easily be able to measure the heat transfer coefficient. But if you can measure both surface and fluid temperatures in areas of interest within the cabin, and then compare those results, that'll allow you to sort of back out the impact of the heat transfer coefficients and how accurate they are with either simulation type. It is important to note that just in the same way that heat transfer coefficients from CFD models with different resolutions, don't necessarily compare numerically. Same is true with RapidFlow. So it's often important to not just directly compare the values of heat transfer coefficients, but look at the bigger picture of the convective heat flux and the nearby fluid and surface temperatures.
All right, thank you. Is it possible to compile the RapidFlow model into an FMU with embedded solver to be used by an external 1D tool for co-simulation?
Yes, that is what we were illustrating a couple slides back using the input parameters. So you would start with your TAITherm cabin model with RapidFlow activated. You would set up input parameters for any of the boundary conditions that you wanted the FMU to be able to change. So those could include the velocity and temperatures at any of the inlet boundary conditions. And then you could add any other outputs as output parameters that you wanted to be able to get back from the FMU. And then it's just a matter of exporting that FMU from the TAITherm application, and that'll give you a model that'll give you an FMU where TAITherm and RapidFlow would be running in the background. And even though it's running as an FMU, the full 3D results are still going to be stored, on disk with whatever FMI application is doing that. So you could even go back and look at more comprehensive results besides the parameters.
All right, thank you. Are there any restrictions on the cell count within the fluid domain?
The only restrictions are really just the amount of memory you've got on the workstation or HPC where you're running, and your tolerance for how long the solution is. Yeah, another benefit of the simplified approach is there are no sort of strict solver limit requirements on how small or large the cells can be. So yeah, like we were saying, I think during some of the slides, it's often just a matter of choosing the level of detail that's needed for whatever the finest geometric details, small gaps are needed, and then choosing the cell size that'll get that. And yeah, given the scaling that is possible on many CPUs, even in the current version before we've got some of those mesh refinement features that I was talking about, if you've got a high number of CPUs, you can still turn around these models pretty quickly, even with a very small cell size. So I think the smallest we showed for this cabin example was only about 18 millimeters, but it's perfectly practical to go down to 10, 5 or smaller, especially with a high CPU count.
All right, thank you. Is it possible to perform coupling for a specific interval rather than a time step, either explicitly or implicitly?
I'm not sure I fully understand the difference between a specific interval and a time step, but to elaborate a little bit about how that works, the TAITherm thermal model time step size is still specified in all the ways you can for a model without RapidFlow. So you can have a constant time step size, a time step curve, or even that adaptive option based on changes in the surface temperature. And then for whatever each of those thermal time step sizes are, you have these different options for how far RapidFlow needs to march to be coupled. And you can sort of think of it as starting from a default of RapidFlow will take typically smaller time steps due to the time scale of the fluid domain. But by default, it'll take as many as are needed based on the CFL condition to reach the size of the TAITherm time step size. So if the thermal time step is 5 seconds, and based on the CFL and mesh size used, the fluid model is going to need to take half-second time steps. That there'd be 10 sub-steps before it's coupled. But then you can further limit that duration or use a tolerance to specify that the flow solver does not have to go the entire way, which is especially valuable for larger thermal time step sizes or really long durations. So those are the controls you've got with that right now. Yeah, if there's more questions, feel free to follow up with an email.
Thank you. How is the flow split between recirc and fresh out in the cabin handled, the flow outlets in the system?
Yeah, good question. So yeah, this example, it was 100% recirc and just a single outlet. So that's kind of the simple case. If you did want to split that, you can either have outlet boundary conditions, which are essentially fixed pressure, or you can have an inlet that has flow specified out of the domain, which is a common technique used in a lot of CFD tools as well. So if you wanted to prescribe the split, you could either have both of the outlets or even more than two. You could have them all be inlets and just specify the outflow for each one, or you could specify the outlet for one of them and have the remainder be pressure outlets and just allow them to solve for what comes out. But yeah, you've got flexibility on whether the outlets are calculated or prescribed is what it comes down to.
All right, thank you. Can dynamic boundary conditions be applied, such as during cool down phases with varying mass flow rates or temperature settings? And if yes, can you use thermal comfort to determine the boundary conditions as a closed loop for optimization?
Yeah, interesting. Yes, and our cool down example here, we were only changing the inlet temperatures and not changing the flow conditions. But yeah, you can change both, and you can change them all with the same methods, either prescribed transient profiles with a curve or dynamic conditions based on input parameters. And yes, you could set up a feedback loop based on thermal comfort to control that. Probably the simplest way to do that would be using a Python script built into a TAITherm model. So again, you'd set up those parameters and you could have the Python script read the comfort result from the human model and accordingly change the boundary conditions for the RapidFlow side. And by using the right or appropriate solver settings, the flow solver would merge forward whenever those change appropriately.
All right, thank you. How is RapidFlow different from existing CFD analysis? Can you tell us percent error difference compared to star CCM Fluent?
So of course, big picture, that it's going to depend on the model details for each one. The bar charts we showed for our cool down example, we're trying to give a sense of that trade-off and how it compares, at least for this particular cool down model, with a particular range of cell sizes and duration of that steady initial flow condition, which were two pretty key parameters for this particular example. Of course, even those trade-offs that we showed under those constraints might be different with different models and different geometry and different assumptions made about the many ways that a CFD model can be configured in terms of its mesh and geometry. But I think in general, the way to think of it is that under the most typical conditions, RapidFlow will be substantially faster and slightly less accurate than a CFD coupled solution. But whether that precisely holds true, again, will depend on a lot of model details.
Okay, thank you. Does RapidFlow create prism layers on the solid boundaries?
It does not. One detail that we maybe hinted at but didn't go into detail is that the boundary modeling techniques are also simplified compared to conventional CFD. So because of those simplified flow equations, we're not bound to something either like a wall function or a resolved boundary layer method that you would see in more conventional CFD. And as a result, there are not really any constraints on how fine or coarse the mesh needs to be near the walls. That, of course, can be one area where the differences in fidelity or accuracy are apparent in terms of, if you're looking at something that really does require a detailed boundary layering method. But part of what we were trying to show in the cabin example here is that, if you kind of step back and look at the results of those flow predictions in terms of, how they affect thermal predictions, comfort predictions, things of that nature, there may not always be a strong dependence on those high fidelity boundary layer modeling techniques.
Thank you. Are the runtimes quoted with a one-time flow solved at the beginning? Thinking of a system simulation where the blower/register flows change in time and how that would impact runtimes.
Yep. Yeah, for our cool down example here, they were all frozen flow with just an initial flow field calculated upfront for both the CFD and the RapidFlow variants of that model. And yeah, of course, for a more dynamic condition, that's going to affect things. So, to make that practical, especially if it's a highly dynamic sort of blower condition that's fluctuating or changing pretty frequently, and you want to capture that, that might encourage you to either use a coarser cell size or to use some of the pseudo transient parameters to try to balance that. But again, hopefully we see it as a good match for that kind of 1D coupling case due to the ability to tune those parameters and use the right level of mesh fidelity or other parameters to get that right. But yeah, certainly when you're solving a full transient coupling with all the flow equations and not just the thermal field, it's going to be slower in general.
Thank you. Does coupling with FMU require cotherm?
It does not. Yeah, the FMU export feature from that, the export action is taken directly from TAITherm, and that gives you an FMU file that can then be brought directly into any system tool that supports importing FMUs. That FMU is still dependent on a TAITherm installation and a license, so it's not a standalone FMU in that sense. But yeah, that particular coupling method is independent of cotherm.
Okay. And what are the timelines for future releases?
Yep. So as mentioned, the time frequency is twice a year with the TAITherm releases in April and October, and the main focus for next year's April release, so that'll be version 2025.1, will be this boundary refinement feature. That's still in development enough that the exact capabilities we'll have during that release are somewhat in flux, but that'll be one of the main things coming out with that. And alongside some of those larger things I mentioned on the future, there's small things we'll be slotting in alongside those bigger ideas. And yeah, we don't have strict timelines for some of the other features beyond that. And to some degree, we're still making decisions based on customer feedback on when some of those will come. But I did hit on, I think, some of the other key ones that we'll be focusing on later in 2025 and 2026, including the moisture capabilities and GPU acceleration. And yeah, if there's more interest in the specifics of that, and so happy to chat more on the details of what we know if you want to reach out further.
All right. Well, looks like that's it for questions. So that will complete today's webinar. We appreciate you all attending. You will receive a follow-up email this afternoon containing links to download the presentation slides and watch the recorded webinar session. Again, thank you, Josh. Thanks, everyone, and have a nice day.
Thanks, everyone. Bye.